Good morning all, this is Swapna. Welcome to machine learning video. Today's our topic is backpropagation algorithm. Introduction of backpropagation algorithm is given in previous video. We are continuing with the algorithm today. So this is the backpropagation algorithm. To understand this, first we need to understand this. This is the multi-layer network. In this it is having that first layer is input layer which contains the source nodes, and last one is the output layer. It contains the output neurons. In this multi-layer networks, to apply the backpropagation method, to find the error, we are taking that output as a combination of output neurons, and also we are finding that error summation of half of the all the output neurons squared difference between the target output and whatever the output we got through the simulation of training examples. Here once we found the error at this point, here it is the error we found, means this may be the error may be the chance of in previous layers also, because these outputs got the input from these hidden neurons. For this output neuron, these are the input source neurons, and whatever the weights here we are applied, that are on this here. And if you are getting the error here, means we are finding the change of weights and we are updating the whatever the weights are here. But there may be a chance of error here is because of these neurons. These neurons are acting as output neurons for these input neurons. These are getting the input from these input neurons, these source neurons, and whatever the weights here for this is applied on these input signals is here. Once you got the error, first we need to find out the change of weights. After that we are updating this one. Here also we are finding the notion error from this output. Whatever the here we are also finding the notion error. If there is error, we got the error because of error of this time, because of whatever the weights randomly applied here, because of that only if you are getting this, we need to update these weights also. That means whenever we got the error, to what is learning rule? Updating the weights. By updating the weights only we are calling as a learning rule. To update the weights in this backpropagation method, first we will find the error at the output layer, and it is having the one or more hidden neurons. Here we are considering the multi-layer network. One or more hidden layers are there. So that's why we are going back, and we are also finding that the error is there. Then we are updating the weights. If there is no error at this point, only because of these weights only if you are getting the error at last, means we need to update this one only. We will check this. If there is no error, means these weights are perfect, no need of updation. So that's what we are doing in step-by-step procedure. That means we are finding the error here first. After that we are finding the error for these hidden neurons also. Here also we are doing the same summation. There is some error, minimum, there is a error is there, then we are updating these weights also. That are we are giving in step-by-step procedure. That is here. This is the backpropagation algorithm. For this, input is training examples, and eta is the learning rate parameter, and remaining in what is the particular neuron output, particular neuron input, and how many hidden neurons are there. Each training example is pair of that we already know input signals and with the target desired output. X is the vector of the network input values, and T is the vector of the target network output values. And eta is the learning rate, already we know. And this value here, initially what they are taking is initially eta value or learning rate parameter is 0.05. And N in is the number of network inputs. I already told N in input is number of network inputs. N hidden is number of units in the hidden layer, and N out is the number of output units. These are the input units, these are the hidden units, and these are the output units. The input from unit I to J is denoted as like this, and the weight representation on this input signal is WJI. It is from signal or connectivity from I unit to J unit. Here we are creating the feed-forward network with the n input units and n hidden units and n output units, and initializing for all the network weights to some random values. Whenever we are constructing the multi-layer network, generally we will update the weights with some random numbers. That random numbers weights are from minus 0.05 to plus 0.05. And until the termination condition is met. What is the until the termination condition is met? Means what is the termination condition? Is finding the global minimum error, that we can call as our termination condition. So for each training example, we will continue this loop for this iteration and propagate the input forward through the network. For the input instance, X is given to the network and computing the output for every unit U in the network. Propagating the errors backward through the network. We are finding the errors, and here in this back-propagation method, error representation is given with the delta. For particular output unit K, calculating the error time is delta K. Here this is the error time. How we are getting this? Already we gave the formula of error for this back-propagation algorithm. By the derivation of that, we will get the conclusion part here like this. What is the error formula means? This is the error formula for the back-propagation. Summation of all the training examples, summation of all the output units. What is the squared difference between the target output or desired output from that simulation output? By taking the derivation of this, that is represented here like this. That we got this one. And after that, we are going back and we are finding that, calculating the error term, that is represented with delta H. Final output error term is represented for each output unit. Error term is delta K, and for each hidden unit is represented with delta H. And for this, what is the error term is like this. Here this is the final error term, what we are getting here for this particular unit, and also it is summationing it is downstream of this one also it is considered. Next layer, output layer. And after this, every time we need to update the weights. How we are updating the weights means by this formula. This is the previous weight, and whatever the change value you want to update, that is delta WJI. And how we are finding the delta WJI means here by this. Delta WJI is neta delta J. Delta WJI is neta delta Ji and XJI. This is the formula for delta WJI. That is means input is from I node and J is the output node. So whatever the updation you are required for that particular input signal, this is the formula. Eta is already we know learning rate. Delta J means whatever you are finding this net summation of that errors and that particular input signal on that particular input signal. So this algorithm applies to the layered feed forward networks. We already said feed forward means every time it is feeding the inputs in forward manner for the next layer. It is taking the inputs from the preceding layer outputs, Here for this algorithm, what we consider is containing two layers only. That's what I shown in your figure, which these two layers are containing the sigmoid units. Each layer are connected to the units of previous layer here. These are sigmoid units only, and all are from input layers. Here these output neurons are also connected to the preceding layer neuron units. So back-propagation, what are the notations we used in this back-propagation algorithm is, index given is with the integer numbers like j, I, all per particular node, index is given, and like this xji denotes it is input from node I to node j, and wji we already told you it is representation for the weight, and delta n is it denotes the error term. That's what it is, the error term delta n. Here to understand that here we are applying the back propagation method, error term is represented with the delta symbol, and what we are taking minus of derivation of that error term with the all the net output units. So here constructing the network with the desired number of hidden and output units, initializing all the network weights to small random values. That's what we given in the step of the back propagation algorithm. We are initializing all the weights to the small random numbers, and according to the network, we are taking some number of hidden neurons and output units, and this we are considering as a fixed network structure, and every time we are iterating this one all over the training examples to make it as perfect. We are iterating through all our training examples, and calculates the error of the network for network output for these examples, and depending upon that error we are updating all the weights in the network. And here we will find the minimum error one. Gradient descent update rule only we are using, just like the delta training rule. We are using same thing as a basic for this. And weight update loop in back propagation algorithm iterates through the thousands of times in a typical application. It iterates through the thousands of times till it will get the perfect one with the global minimum value, with the global minimum error. Till that time it is iterates thousands of times. Here I said in this algorithm directly we wrote that derivative values. These are the derivative values. Here we wrote directly derivative values of this particular output unit, and also after the derivation only we wrote these values for the particular hidden unit only. Here we are finding the derivation of that one. So this is our formula, normal error formula for this gradient descent. What is that stochastic approach of gradient descent is like this, of summation of all the outputs and the difference between the target output and whatever the output we got. So here we are applying the chain rule to find that. Actually we need to find the error with respect to the what we can say parameter of the hypothetic space. That is parameter is weights only. For a representation, visual representation of hypothetic space, what we use the parameters, error is one side on the y-axis, and on the x-axis we will use the weights. So these are only the hypothetic space parameters. So that's why to find the derivation of this one, derivative of this one error, we are finding the derivative with respect to the weights. So by applying the chain rule, this we are finding the derivative of ED with respect to the net j, and net j with finding the derivative of net j with respect to the weight. And this we can write as like this. This part we can write as j of this one. And whatever the notations here we are using, here we are once again I am explaining this one. Xj is the already we know ith input to the j unit, and wj is weights associated with the ith input to the j unit. What is net j? Net j is the linear combination of inputs with inputs that here represent. That is why the before sigmoid unit, before applying to the particular function, what is the linear combination we are taking with the adder, that we are specified here as a net j. OJ is already we know output computed by the j unit. Tj is the target output for that particular j unit. Its sigma is already we know that is sigmoid function, because in that layers whatever the neurons we are using, that are the sigmoid units. So this sigma is represents that one. Outputs means it is the final output. What is downstream j? The set of units whose immediate inputs include the output of unit j. What are the outputs we are getting at the j neuron? That is given to the inputs like to other unit. That we can call as a downstream of j. If it is that particular neuron is in the hidden layer, that output is given to the output neuron. That output is given as input to the output neuron. That is we are representing here as a downstream j. And then we now derive an expression of this one, error with respect to the weights, to implement the stochastic gradient descent rule. To begin this, first what we are using this net symbol. So we are considering to find that two cases we are considering. First one is we are finding the train rule for output unit weights. After that we are finding that rule for hidden unit weights. Here we need to find the training rule for the output unit weights. Here it is like this: derivation of error with respect to the first term. In this, what is the first term? Error with respect to the net. Second term is net with respect to the weight. So that's what we are finding this. Here it's first term with respect to the net. That is, once again we are applying the chain rule here. Then this error is, we are finding derivation of this error is with respect to the output, and derivation of output with respect to the net. So to begin this one, we are replacing this error term with this formula. Within this also we are considering the first term, derivation of error with respect to output unit. So this one with respect to output unit is half of that, replacing with the formula of square root of this one generally. So after that we are applying the derivation. So the derivatives of this will be 0 for all the output units k, except when k is equals to the j. So therefore we drop the summation over output units, simply set k is equal to j, and we are writing this one. First derivation of this expression we will write like this: 2 into tj minus oj, and derivation of tj minus oj by with respect to output unit. Then we will get this term. It will cancel this and this, and derivation of this term we will get same as it is this one. So this with respect to output means it will become as a 1. So we will get this. Next, consider the second term. So what is the second term here? Is the derivation of output unit with respect to net term. So we are considering that one with respect to net. Simply we are replacing this one with the sigmoid unit. That is, here we are applying same thing. We are replacing this with the sigma of, it is equals to this one, which is replacing with the oj is sigma of net j. That by the derivation what we will get like this. So that we are replacing this one and we are getting this term. After, by substituting these two terms, whatever the two terms are there, by substituting this, what we will get? Derivation of error with respect to net is that we get here like this. Derivation of error with respect to net, we will get complete term like this. Next, now we have the, what is the change of weight? Gradient descent rule. What is the output change of weight is like this: neta into derivation of error with respect to w with respect to hypothesis parameter w weights. That we are substituting here. This we will get last one. So this we got this one for this output unit. Next, second case is the training rule we are finding for the hidden unit weights. Here we are considering this one. Net G can influence the network of output only through the units of downstream G. We already know what is downstream G. So summation of downstream and E error with respect to net, and net with respect to net of K with respect to net of J. And that we are writing as like this. This one is completely delta K. Whatever we found till now, that we can completely, if it is representing with this delta K. That is, we are replacing. Now we need to find this one. To find this one, once again we are applying here chain rule. That is, delta net K is with respect to, we are finding delta Oj, and here second term delta Oj, we are derivation of delta Oj we are finding with this delta net J. That is, we are replacing this one with the chain rule. By applying the chain rule, we can write this term. This term we can write as this. After that, once again we are replacing with these two. Whatever we found already with this, that is, we can replacing with the WKJ, and this one. This one also we found with the previous case one. That we are replacing with this. So completely DJ, what is hidden term error is represents like this. Generator term is represent like this. Whatever the second term is there, first term we are writing like this. So this is the weight application for the hidden unit. So we said so many times we are continuing this point before the derivation. Whatever the point we said here is last point. So this one, the weight update loop in back-propagation algorithm, we iterated thousands of times. Here, if it is continuing like this thousands of times, no need of that one. Where we can stop. That here we are giving a variety of termination conditions can be used to halt the procedure. To halt that thousands of time iteration, we can stop that one. These are the first choices. Halt after the fixed number of iterations. Here we are considering some fixed number of iterations. We can halt that one. We are fixing that one loop condition with some fixed number. After that, it will automatically stops the iteration. Or one more thing. Once the error on the training example fall below the some threshold. Otherwise, we can keep the some threshold value. Some threshold value. If it is falls in between that error value is falls in below that some threshold value, it can stop the iterations. Once the error on the separate validation set of examples meet the some criterion. Here also we can say one more thing, some criterion. Like in our real-time example, students have the passing marks. Generally, if they have the knowledge means you will get the full marks. Otherwise, at least approximate full marks. Instead of that also, every student is promoting to the next year after the some threshold point. After the some threshold point. That is we can call as a passing marks. Here condition is passing marks. If you got some minimum number of pass percentage, then you can promote it to the next class. That is considering as a enough knowledge required to promote to the next year. That we can call as here threshold. Second choice of termination criteria is important one. Here this choice of termination, whatever the choice here we are taking, this is the fixed number of iterations or some threshold we are keeping or some criterion on the validation set also we are keeping. But choice of which choice we are taking, that choice of termination criteria is also important one. Because if you are taking the few iterations only, here in the fixed number, when we are taking the choice of fixed number, to stop that fixed number, we are keeping that some fixed number. If you are taking the less, few iterations only, then it may lead into the overfitting of the training data. Then it may lead into the overfitting of training data. So, by this I am concluding this part. So, in next part, we can go for the remarks of the back propagation algorithm. We'll meet in that video. Thank you.